Good morning, friends. This is prof.a.k.chaubey. Prof.chaubey's first class. Today, I will talk about the interference. In fact, we will do some problems of interference of light. We have completed the interference, analytical treatment of interference. So let us do some problems for that. I have problem number 1. In Young's double slit experiment, the distance between the slits and the screen is the distance between the slits and screen is, say, 1 meter. If the distance between the slit is 5 millimeter, if the distance between two slits is 5 millimeter, and the fringe width is how much? 0.1092 millimeter. Now calculate the wavelength of light. So friends, this problem is simple formula based. You have the formula, you are given the distance, that is the, formula that beta is the fringe width, is given by lambda d over d. And here in this question, you know that d given, d is equal to small d, the slit distance 5 into 10 to the power minus 3 meter, and capital D is equal to 1 meter, and beta is equal to 0.1092, that is millimeter, so into 10 to the power minus 3 meter. Now all these parameters are known, so you can find out lambda. Lambda is equal to beta d over capital D. So just substitute the values and find out lambda. That is, you can get lambda is equal to, so substitute all the parameters, 5 into 10 to the power minus 3 small d, this, and beta, beta is equal to, and divide by capital E, that is 1 meter, plus beta. Beta is how much? 0.1092 into 10 to the power minus 3. This way you can get the lambda. Well, lambda will be about, lambda, you calculate this, multiply 5 this, you will get 5460 into 10 to the power minus 10 meter. or 5460 angstrom. So friends, this was just simple problem. As I told you that you have the expression for fringe width in terms of lambda and capital distance of the slits on the screen and small d distance between two sources made from one light, one source by Young's two pigeonholes, and also maybe by some other device like by prism. You can make two, one source converted into two coherent sources. So that is small d. So put all these parameters, you get the lambda the wavelet. Well, this is the very nice experiment for the measurement or laboratory experiment for the calculations of wavelengths of optical source. Let us do some more problems like similar type. In a Young's experiment, in Young's experiment, what experiment? The separation of four bright fringes is the separation of four bright fringes is yes 2.5 probably is 2.5 millimeter, and the wavelength used is wavelength of light source is 6200 angstrom. So wavelength is given, and the distance from the slit to the screen is distance between slit and screen is 0.8 meter. Calculate the separation of two slits. Friends, this is simple again substitution of the different values, and you have to calculate the distance between two slits, small d, and other parameters are given here, that is beta is equal to, we know, lambda d upon d. So use this formula, and we have here lambda is 6200 angstrom, so 10 to the power minus 10 meter. Lambda is given, and you have d 0.8 meter, and you have, say, beta 2.5, beta is given 2.5 millimeter, so 2.5 into 10 to the power minus 3, but this is the width of the four bright fringes, so one fringe means beta, that is divided by the 4. And now you substitute everything and get the result, get the d. D is equal to, here, lambda d over beta. Well, so you put all these parameters, 6200 10 to the power minus 10 lambda, d is 0.8 meter, and beta is 2.5 into 10 to the power minus 3, and that into 4. So solve this, you will get small d, multiply this, you will get the value of 0.8. First you will get in the meter, that you convert 8 into 10 to the power minus 4 meter equal to 0.8 meter. 0.8 millimeter. So this is simple, again simple substitutions of various parameters in the mathematical formula, and you can get very easily the whatever. We have 4 small d, capital D, lambda and beta, and you are given 3, you can get 4th. So just different types of problem you can get. Out of 4 parameters, 3 must be known and 4th you can calculate. That's simple mathematics and nothing else. So like this, you can solve the problems. You can solve other problem also. Problem 3 is in Young's experiment, lambda is equal to 5893 angstrom. 62 fringes are observed. 62 fringes are observed. Sixty-two fringes are observed in the field of view. If source of light is changed, to lambda equal to say 4358 angstrom. Now the question is, how many fringes will be observed? How many fringes will be observed? Well, this is the typical question here. Usually here one source of light is given and we observe on the screen the fringes, black and white, black and white. We count how many, say white color or black, because both are equal bits having, so you can count any. So just count bright, 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 bright. It is found that 62 fringes are observed. But they change our light source to this. So what will happen? Because small d, capital D remaining same, just lambda is changed. How many fringes will be observed? So just you calculate the fringe width. Fringe width you know. So how total screen? The first problem is, 62 fringes are observed. So 62 into beta. Total is beta is the one fringe width, so 62 fringe total that comes. 62 beta, that you find out how much 62 beta. This will be equal to how much? Beta is equal to lambda capital D by small d. So that is 62 and d lambda over d. So that you can find out lambda, 2 lambda, and then you have how many, this is 62 beta, say x beta fringe, x fringes are observed. and or n, yeah, n you write n, n fringes are observed with lambda prime, the new wavelength. So you have n into beta, yes, or you have say n, how many fringes? The n d lambda over d, the total distance screen, this lambda prime, and this is 62 d lambda over d. Just because screen remains same, the view. So n fringes are observed, then n d lambda over d. Here it was 62, so 62 observed. So 62, and then this remains same. This lambda prime is changed. Others can be cancelled. So you can find out that lambda prime and lambda both are given. So lambda prime is given, lambda is given. This d and d and d and d is cancelled here. Well, n is equal to 62 lambda over lambda prime. So 62 and 2 lambdas, 5, 8, 9, 3, and lambda prime 4, 3, 5, 8. Just simple. So and you get how many fringes are observed. You calculate this 62, 5, 8, 9, 3, and you get the answer 84. So when you change the light source from 5893 angstrom to 4358, the fringe width, the number of fringes increases, more fringes are seen. Because light is changed, so fringe width will change, but total screen is n times of that. So we get, this is the fringe width, n times this is the fringe width 62, but total remains same, screen where you are observing. So that means you equate this total, you get the value of n. Okay. This way, one can solve the problems very easily. The formula-based problems are there. Yeah. Anything other important thing is what as we can discuss, we can get some problems, objective type problems are there, say while two coherent sources produce two current sources produce a dark fringe when phase difference between the interfering waves is, when the phase difference between interfering waves is, say, here n is integer. Zero, phase difference is 0, 2, 2 pi, 3, n pi for 2n plus 1 pi. Now you have to think on this. This is the problem. 1 minute think on this. What the problem is, what the answer will be. What they ask, the question is. Question is that two coherent sources produce dark fringe. Destructive, and we have analytical formulas that when the phase difference, it is the phase difference, angle, phase difference is 0 or 2 pi or 4 pi, that is the integer multiple, even multiple. Then we get same phase, both waves are in the same phase, it will be constructive interference. So maxima are there. Here we are finding the dark fringe, means minima. So maxima of one wave is falling at the minima of the other. So resultant becomes 0. Because both waves are of same amplitude, so dark fringe. Because it is produced from same source. So now it should be odd multiple of wavelength. Also in terms of angle, phase difference, they should have opposite, means phase difference pi, 3 pi, 5 pi, 7 pi, like that. So this question is zero phase difference. Zero phase difference means both are, zero means both waves are like this, coinciding. So this is not possible because it will be maximum. 2 pi means just after this, again both waves start here. So this 2 pi means also not possible. N pi means pi, n is 1, 0, 1, 2, pi, 2 pi, 3 pi, 4 pi, 6 pi. So this is also not, because we have here 0, 2 pi and 3 pi. What we see? 2n plus 1. So 2 and n is 0, it becomes 3 pi. N is 1, it becomes, sorry, n is 1, n is 0, it becomes pi. N is, in general, 1, it becomes 3 pi. N is 2, it becomes 5 pi. So odd multiple for destructive interference, phase difference should be pi, because it is here. Destructive means this is like this. So when this wave starts here, the other wave starts from here. This is pi. So then they are just opposite. So it should be pi. Then if it 2 pi, it will be bright. So 3 pi, 5 pi, it means it should be odd multiple of odd integer. So odd means 2n plus 1. So this is the correct answer. We got 2n plus 1 pi, odd multiple of pi for dark, and even multiple of pi for bright. So this is the answer. You know you understand what the meaning of dark fringe is. That is the destructive interference. Means both waves are opposite phase, just opposing each other so that the amplitude becomes 0. Okay. Then we have a double slit experiment is performed in air. The whole apparatus the whole apparatus is immersed into water, what will be to fringe width? Answers are given here. Increases, decreases, and remains unchanged, and fourth is fringe pattern disappears. What will be? So what the answer of this should be? Fringe pattern disappears. No, why it disappears? The whole setup just, you have changed the media. Media means you have changed the refractive index, mu. So this remains same, no, unchanged, remains unchanged, no, this is not. Increase means fringe width becomes wide. If the density of the media decreases, it becomes rarefied, then it will be increased. If the media is denser, means water is denser than air, the fringe will be narrow, shrink. So this will not be the correct. The correct answer is decrease. The fringe will be narrower. The width of the fringe will be decreasing. Okay. Now, similarly, we do some more problem. Say, what the number maybe 4, light waves are what are the light waves? Light waves are electromagnetic waves, that you must be knowing. In nature, light waves are electromagnetic waves in nature. 2, well, light waves are cosmic, infrared, none of the above. Well, you must be knowing the light wave nature. It is none of the above, not correct. Infrared, only infrared not. It is ultraviolet also, visible also. Cosmic, these are cosmic particles. Cosmic is no. Electromagnetic in nature means light waves are where electric and magnetic vectors are vibrating perpendicular to each other and they propagate in the medium. Electric field and magnetic field. So that is called, all the waves like that, gamma rays also and photons, they are electromagnetic waves in nature. They can be produced by the oscillations of charge. Oscillations of charge oscillate means electric field changes means magnetic field changes. Magnetic field changes, electric field changes. So oscillations of electric and magnetic fields, they produce electromagnetic waves. So light waves are electromagnetic waves in nature. You must keep in mind. Light waves are electromagnetic waves in nature. More questions? Similar type of questions you can do, numerical questions you can do. I am just giving few examples only. I can't do more. Just I have to give knowledge of all. Say, okay, ask. Just I answered the question, the whole setup is immersed in water. I told you that medium changes, wavelength will change. So wavelength change that I told you, the fringe width, the wavelength of the light is less in water. So wavelength becomes less. So wavelength less means the width decreases. The question is now, when the wave interferes, one wave the other wave are just opposite, amplitudes of two, we get darkness. Means the energy media displacement becomes zero. So when there is no displacement, where the energy goes, it becomes zero. So energy is not zero. Two waves are propagating and the interference we get darkness. So the answer is that the energy of the minima, darkness, goes in the maxima. Because maxima becomes double, 4I square. So the energy where it becomes dark, that light, that energy shifts to the maxima. Because maxima increases. So darkness energy goes to the brightness, so that it is the high, obviously. So friends, I think you should do more and more problems, more and more questions of this type. Say, in the young slit experiment, only one slit is observed. Only one slit. In the young double slit experiment, one slit is covered. What will be effect? We have two sources. Two sources means two current sources, two waves, they interfere. When it becomes one slit is covered, only one slit is there, the phenomena observed is not interference, it becomes not diffraction. So we will talk diffraction maybe later on, what the diffraction is. We stop interference here now and we will talk. That one slit is closed, only one slit is there, the pattern will be what type of pattern, what we will get, and that's called diffraction of light. So friends, I stop here. Thank you very much.